Okay, let's do this. So right-hand rule. So direction of current, again, is your finger, your pointer. Direction of magnetic field is your middle finger. And then your thumb is the direction of the force. And so the current is to the right. The magnetic field, wait, what? Oh, they're in the same direction. Notice they're in the same direction. This doesn't work. There's no force. So remember my equation for force, magnetic force for a moving charge is QV cross B. And so if the velocity and the magnetic field are in the same direction, this term goes to zero. Because again, V cross B means VB sine theta. VB sine theta. And here, the angle between the velocity vector and the magnetic field is zero, so sine of theta is zero. And this one we can do. So the direction of the motion is here, the direction of the magnetic field is to the right, so the force is into the page. That's the direction of my thumb, into the page. So X. The direction of the current is to the right, the magnetic field is this way, so the direction of the force is out of the page. So this is out of the page. Velocity into the paper. So velocity into the paper. So we're going into the paper, magnetic field is this way, so the force should be up. But it says here it's a negative charge. So for negative charges, you just flip everything. So the force isn't up, it's actually down. Down. South. Okay. Magnetic field out of the paper. Okay, so motion here, magnetic field here. The force is downwards. South. Did I do that right? Yeah, that's right. Interesting. Okay. Magnetic field into the paper, the direction this way, so your force is this direction. That is northwest. Northwest. Okay. Current out of the paper. So current's out of the paper, magnetic field is this way. Oh, that's really hard to do. Ow. The force is up, north. Magnetic field out of the paper. So magnetic field out of the paper, the current's in this direction, so the force is up and to the right, but this is a negative charge. So that means you flip everything. It's not up and to the right, it's down to the left, southwest. Next. So we have a proton moving, that's a positive charge, so we know the direction of the force with the right-hand rule. It should be upwards. So the magnetic field's into the page, the motion is to the right, so your force would be upwards by the right-hand rule. So there should be a force to the right, force upwards. Now sometime later, it's gonna be bent, it's gonna change directions. And so, I don't know, let's imagine it is here. And it's moving in this direction. I'm just kind of ballparking this. So if it's in that direction, the force is up and to the left a little bit, perpendicular. Notice the force is always perpendicular. So this is force, this is velocity. I should label that force velocity. This will cause a bend. This is circular motion. You learned this last year. Let's imagine the velocity is this way. The force would be up and to the left, but again, perpendicular. And you'll notice I can keep on doing this. I'm just kind of ballparking. Velocity, the force would be down and to the left. And I can keep on doing this. And so while we're in this magnetic field, notice we're moving in a circle. And something else to keep in mind, notice the velocity is perpendicular to the force. That means, so velocity and force are perpendicular. That means two things. One, circular motion. That means that constant speed. So remember, to slow something down, you need a force opposite the direction of motion. To speed it up, you need a force in the direction of motion. And that also means that there's no change in energy. And that's the really weird one. So we say that there's no work being done. No work done. So there's no change in energy because the velocity hasn't changed. So, sorry, because the speed hasn't changed. And remember, my equation for kinetic energy is 1/2 mv squared. So since V squared is going to be the same for all of these situations, the kinetic energy is the same and no work is done. Magnetic fields do no work. That's going to be super important. Magnetic fields do no work. Yeah, that one's, I'm sure, going to come up. They only change the direction, but they don't do any work, which is kind of cool. Okay, cathode ray. So this is a negative charge. So let's imagine the charge is moving this way, and I want to force downwards. So that means the magnetic field would have to be upwards towards you, but this is a negative charge, so everything's flipped. So the magnetic field shouldn't be upwards, it should be downwards. So we need a downwards magnetic field in this direction, in this manner, to deflect this thing. How do you create this magnetic field? Make a big solenoid, lots of ways to do it. What direction? Okay, we want the deflection to be out of the paper, so I want the force to be out of the paper, and the direction of the current is to the right, and so the magnetic field needs to be up. But that would be true for a positive charge. This is a negative charge, so everything's flipped. So the magnetic field needs to be down. B is down. Okay. Into the paper is the magnetic field. The velocity vector is up, so the force is to the left. Sketch the path. And it actually makes a circle, or a semicircle. Once it leaves this magnetic field, it won't be the case. So the force is to the left, and then it's always kind of perpendicular to the motion. Now for negative charge, everything would be flipped. The force isn't to the left, it's to the right. Yep. It's easy. Next one. Okay. On segment 1, so current goes this direction. I'm just going to draw it just for simplicity. Current goes from positive to negative part of the battery. Okay. And so for segment 1, notice the current and the magnetic field are parallel to each other. No force. And the same thing is true for 3. No force. The current and the magnetic field are in the same direction. They have to be perpendicular in order for there to be a magnetic force. What about segment 2? So segment 2, the current's going up, the magnetic field is this way, so there's a force downwards into the page. For 4, the current is, just move the paper. The current is in this direction, the force is, the magnetic field is this way, so there's a force upwards out of the page. So what's gonna do? It's gonna rotate, yes. For a little bit, at least. In which direction? Well, this is feeling a force out of the page. This is feeling a force into the page. So it's rotating like this. I don't know how you describe what direction that is. I have no idea how you describe that direction that is. From the perspective of the battery, that would be counterclockwise. From the perspective of the battery. Now, it won't make a full turn, and you can kind of think about why that is. It won't spin constantly because it's going to be hard to see. But when 4 reaches this point at its highest point, really high up, the current's still this way, the magnetic field is this way, it feels a force upwards. But it's already up. So that's not going to cause it to turn more towards this way. It's not going to cause it to flip this way. And same thing is true when 2 is at the bottom. It's going to feel a force downwards, but it's already at the bottom. So this thing is just going to flip like this, I think. It might move past it. It might oscillate like this. That would probably be my guess. It would probably oscillate a little bit more just because of some energy stuff. It might like oscillate like this. Now that I think about it. But it's not going to make a full turn. But this is kind of the basics of how motors work. Motors spin. There's some changes you can make to this to actually make the thing spin in a complete circle. But this would not spin in a complete circle. I think it should go like this, now that I think about it. Okay, that's it. Okay, worksheet 3, let's do it. Oh, math. Okay, yay. Numbers and calculator. Okay, straight wire, 50 centimeters long, so that's a length. Current is I. the page. Okay, so that means they're perpendicular, so that's going to be key. And here's the force. And I just want to know what is B. This is just a plug and chug question, really. There's no thinking here. You're going to use this equation. Oh, no, wrong class. ILB. So the magnetic force is equal to ILB sine of theta. I'm going to ignore the integral because like everything's kind of a constant, so I can just ignore it. ILB sine of theta, because that's what the cross means. In this case, the sine of theta, since it's perpendicular, is just going to be 1. So it's just ILB. FB is ILB. And if you just plug in your numbers and do some math, you'll get an answer. I'm not actually going to do the math, but I'll plug in numbers for you. Why not? I is 6. L is 50 centimeters, which is a half of a meter. And then B is what you're trying to find. So solve for B. 30-degree angle. So that means theta is equal to 30 degrees, I think. This is L. What is the force acting on the wire? So magnetic force, again, is ILB sine of theta. So I'm just going to plug things in. I is 15 amps. Wow, a lot of current. L is 0.75 meters. B is 2 times 10 to the negative third Tesla. And then sine of 30 degrees. So put that in a calculator, you should get an answer. Okay, perpendicular. Beautiful. Circular path. Okay, what's its velocity? Oh, this is actually, there's a few things going on here. So first we need to find a force probably. So this is a magnetic field B. So we need to find the force. And I'm going to use this equation. This is the force for a single charge moving, QV cross B. So the magnetic force is QV cross B. And again, if the velocity and the magnetic field are in the same direction, V cross B just becomes VB, because the sine of the angle becomes 1. So the magnetic force is equal to QVB. Okay. Now, how do you take apart this? You need to remember some things about circular motion. So in terms of circular motion, I think your equation sheet only has this one. Centripetal acceleration is v squared over r. So that means the centripetal force would be, yeah, it doesn't say it anywhere here. Okay, I guess you just have to remember it. Centripetal force would be, where's F equals ma? Where's F equals ma? Oh, here it is. So centripetal force would be acceleration times the mass. So mv squared over r. So that means this is going to equal mv squared over r. If you do a little bit of math, you'll see that the velocity is going to be equal to qbr over m, I think. And this would be, this is actually more of a speed anything because the velocity is changing. Or you can, I guess you can say which direction it is. That would probably be good. Where m is the mass of a proton. Again, the mass of a proton is given to you. It's right here, proton mass. Q is the charge of the proton. The charge of the proton is given to you. It's called the elementary charge. B is here, and then R is right here. So this is R. So just plug in. This, you're going to see a bunch. Like, you're just going to see it. Because these are cyclotrons and pretty cool stuff. Okay, this you can either memorize the magnetic field of a wire, or you can solve it. I'm just going to solve it, just for funsies. And I'm going to use this using, what is it called, Ampere's law, which is here. Which is here. B dot dl is equal to mu naught I enclosed. So let me just write that down. You could just memorize what the magnetic field is, but I am going to not. And I want to find the magnetic field from due to A. here. So I want to find the magnetic field like right here at this location. And to do this, I'm going to make a Amperian loop. We'll try that again. So my Amperian loop is a circle. It's hard to draw. Of radius r. So of radius r from this little thing. And B dot dl just becomes BL because the magnetic field and this loop are in the same direction. Again, the magnetic field around this makes a circular ring. And that's my Amperian loop I just drew, a circular ring. So B dot dl just is equal to B times the length of this loop, which is the length of the circle, which is 2 pi r. Mu naught I enclosed is just whatever the current is, 10 amps. I enclosed. So that means B is equal to mu naught I over 2 pi r. Again, you can memorize this, or you can just resolve it using Ampere's law. So what is the direction and magnitude of the magnetic field? So let's just plug things in. Mu naught is a number. Against, in your equation sheet. I is 10 amps over 2 pi, and then the radius is 1 centimeter. So what is that, 0.01 meters or something like that, I think. So if you just like plug that in, you'll get an answer. Now, what direction is it? Again, with the right-hand rule, it's out of the page. Out of the page. So your thumb is the direction of the current, and then you wrap your fingers around the wire. Your thumb is the direction of current, and you wrap your fingers around the wire, and we're out of the page on this side. What is the magnitude and direction of the force? Okay, well, let's use the other right-hand rule. The current's this way. The magnetic field is out of the page. Boop. The force is to the right. Away from the wire. From wire A. What is the strength of the force? So for that, we can use this equation. So force is ILB. Fortunately, we can do this because L and B are perpendicular to each other. B is out of the page. So I'm just going to plug that in. So the force is equal to I, which is 5 amps upwards, times L. Oh, what the heck does that say? 20 meters? I'm going to assume that says 20 meters. And then B is this, the magnetic field due to this one. So mu naught times 10 times 2 pi, 0.01. And it should be equal and opposite. Remember, when two objects experience a force, they both experience the same force, but in opposite directions. So this is kind of cool. If you have two current-carrying wires, and the charge is going in opposite directions, they actually push each other apart. Now the opposite is true as well. If you have two current-carrying wires and the charge is going in the same direction, they actually pull each other inwards. And you can use the right-hand rules to kind of figure that out. That's going to be important. You're going to see this again and again and again. Two current-carrying wires that are parallel to each other. We'll see that. It's taking me forever. Okay, let's go a little faster maybe. Two current-carrying wires. Okay. So from this wire, if my direction of the current is into the page, the direction of the magnetic field is like this. It's going to loop around. So I'm going to call this the red one. And so from the red one, we go here. And it's really big because we're close. For the red one, we go here. It's a little bit smaller because we're far. And for the red one, we go here. It's pretty weak because we're very far. And that would make a circle, roughly. I don't think I did the best job, but alas. I need to find a pen. That's a different color. Pause the video. Okay. And what about the magnetic field due to this wire? Let's call it the black wire. Same idea. So into the page with our thumb, and we wrap the fingers around. That's the direction of the magnetic field. So it's kind of the same. Boop. And boop. And boop. Okay. Now what's the resulting vector? You have to add the two up. So there's a lot of ways to add up vectors. I kind of like the parallelogram method. You make a little parallelogram. And you connect from the origin to there, and that's the direction of the vector. Boop. So a little parallelogram. And from there to there. Another way to do it is to do what's called the tip-to-tail method. So you take one of the vectors, and you put the tail on the tip of the other one. And you kind of draw it the same. Boop. And so from here to here is the direction of your resulting vector. Tip-to-tail method. Okay. What the hell is going on here? Titanium. Okay. So the current is 120 amps, so that's I. The length is given to you, and the magnetic field is B. What is the force on the sled? Since everything's perpendicular, we'll use the ILB equation. So ILB sine of theta. In this case, sine of theta is just 1. So the force is just, you multiply those two. You don't have to do any thinking here. So 120 amps, oh my goodness. The length is 0.02 meters, and then the magnetic field is 2 Tesla. So I can actually probably do this in my head if I were not tired and hungry. Yeah, 240 divided by 50. Whatever 240 divided by 50 is. Yeah, 240 divided by 50. 24 over 5. 4.8 newtons is the force. That makes sense. 4.8 newtons. How long must the track be to attain a final velocity of 20 meters per second? Well, we have a force. Did they give you a mass? They did. Nice. When you get a mass, you can find an acceleration. So the acceleration is the force over mass. So 4.8 over 0.01, which is 4.8 with 2 zeros behind it, meters per second per second. Okay. Now, why is the acceleration helpful? Because now you can use one of the big three equations to find what am I trying to find? Speed, velocity. So this one will probably be fine. Velocity, assuming the starting velocity is 0, is simply equal to the acceleration times the time. Oh, that's not what I want to know. I want to find how long the track is. So I need a distance. So maybe this equation will be fine. Distance, no, that's not helpful. This is your friend. The velocity is equal to the starting velocity, which is 0, plus 2a delta x. So velocity squared is equal to 2a delta x. And what I'm trying to find is delta x. Velocity squared is 20 squared. 2 times the acceleration is 4,800, or 2 times the acceleration of 4,800. And then delta x is what I'm trying to solve for. Solve for delta x. You'll get an answer. Electron moves the whole. These are super important. You're going to see this question again and again and again and again and again. Okay? Okay, magnetic force. So the magnetic field is into the page, the electron's moving this way, so the force is up. But wait, it's an electron, so everything's flipped. The force is down. So magnetic is going to be red, and the force is downwards. Okay? Now, I'm just going to label this as FB, magnetic force. Now, let's do the same thing with electric force. The electric field is downwards, so that means the force should be downwards, but it's an electron, so everything's flipped. The electric force is upwards. Okay? Hey, do you see what we can do here? It's possible for the forces to be the same. It's possible for it to move in a straight line, for the forces to balance out. So for this to be the case, the electric force has to be equal to the magnetic force. Electric force is really easy. Remember, if you're in an electric field, the force equation is super easy. It's just electric field times the charge. So E times Q is equal to, the magnetic force for a single charge is QVB, if velocity and magnetic field are perpendicular. Oh my goodness, Q cancels out. So the electric field just has to equal to the velocity times the magnetic field. That's kind of cool. Only velocity matters and the strengths of the two fields. Suppose the electric and magnetic fields are the same, but now the particle entering the slit is moving twice as fast as before. Okay, that's going to be an effect. Electric field won't change. So the electric field is, notice velocity's not there at all. What will change is the magnetic field. FB is now greater than FE, right? And so if I go to my diagram, FB is going to be greater than FE. FE is really small, so it should experience a net downwards force. And it will turn. This thing should turn. Yes, this thing will turn. So this will turn. And if you want to draw the path, you can probably do that. Now, if it's half as before, that means that FE, turned down, is greater than FB. Because again, FE does not depend on velocity, but FB does. And so now it's not going to turn down. This force downwards is weak. We're going to turn up. We're going to turn up. We'll turn up. Okay, and now we actually do the math. So again, the electric field is equal to V times B. We kind of just discovered this. I'm just going to write it out just from, this is the case for the object moved to, for it to move undeflected. So QE is equal to QVB, assuming the velocity and the magnetic field are perpendicular to each other. So what am I trying to find? Magnetic field. So that means that B is equal to E over V. Okay. So I need to find some things to find B. Find the magnitude and direction of the magnetic field. Okay, proton. Okay, so first I need to find the electric field, and they're giving me a potential difference. They're giving me a distance, and electric field's really easy to find. So electric field is the change in potential divided by the change in distance. Change in potential over the change in distance. So the electric field is just 2.5 kilovolts times 10 to the third divided by 0.1, which is equal to 2.5 times 10 to the fourth. And the units are newtons over coulombs or whatever. There's other units as well. So that's electric field. Now I need to find the velocity. How do I do that? Wait, what? Oh, I definitely did that wrong. So sorry. Oh, sorry. It should be 250 volts. This should be 250 volts. 250. So this becomes 2,500. Okay. Now, how do you find the velocity? This is the part where we use to find velocity. Use this to find velocity. So to find velocity, we're just going to use energy stuff. You need to find the potential energy, which is Q times delta V, and set that equal to the kinetic energy. So UE is equal to K, where UE is Q delta V, so it's the charge of an electron, of a proton, times delta V, which is 2.5, so 2,500. And that's equal to 1/2 mv squared, where m is the mass of the proton. So you can use this, I'm not going to do it, to find the velocity, and then you plug that velocity right there. And then the electric field would be that number. That should be it. That should be it. That should be it. Okay, I'm done. I'm tired. I'm hungry. Okay.